Hello, before we start with the CH125-2P material balances or Checal-2 balances, we have to first review on the terms used in problem solving and in operations. So first off, we have the percent excess. The percent excess describes how much is the other reactant excess in relation to the limited reactant. So kung alin ang kung gaano kadami ang hindi naubos in relation doon sa limited reactant. So how to get the percent excess? That's number of moles fed minus number of theoretical moles needed over a number of theoretical moles needed times 100%. So NTO, makakompute mo siya by using the limiting reactant. Okay, so to get the percent excess, or to basically to start the solving, you need to find what's the limiting reactant and the excess reactant. Next is percent conversion. So percent conversion simply describes the number of moles of the limiting reactant or the reactant that is turned into the product. So it's the number of moles reacted over the number of moles of fed, or this number of moles reacted is also equal to the number of moles fed minus the number of moles remain after the reaction over number of moles fed. So percent conversion is based on the desired chemical reaction, because there might be instances that there are two separate chemical equations like that. So one is desired and one is undesired. So the percent conversion is always based on the desired reaction. Next, we have the percent yield. So percent yield is just the ratio of the product actual, the number of moles of product actual over the theoretical number amount of product. So this can be obtained from the chemical equation. And then we have the selectivity here. Selectivity is very simple. It's the number of wanted product over the number of moles of unwanted product. So I have examples here para mas maintindihan kung ano yung mga pinagsasabi ko dito. Okay. So example 1. Acrylonitrile is produced in the reaction of propylene, ammonia, and oxygen. The feed contains 10% bimole propylene, 12% ammonia, and 78% air. Fractional conversion of 30% of the limiting reactant is achieved. Taking 100 moles of feed as basis, determine the limiting reactant, the percent excess of the other reactants, and the molar amounts of all product gas constituents for a 30% conversion of the limiting reactant. Okay. So let's draw the system first. Okay. So this is my reactor. Going in is 10% by mole propylene, that's C3H6, 12% ammonia, and 78% air. But air is composed of 79% N2 and 21% O2. Okay. In the effluent gas, yung product stream, there will be C3H3N, yung acrylonitrile, H2O. So since not all of the limiting reactant is consumed, we can safely say that these three will be on the product stream as well, kasi hindi sila naubos. But we still don't know sino yung limiting reactant. Okay. Letter A. F. This is P. Basis. 100 moles of F. Okay. Let's start. A. the limiting reactant, which is the limiting reactant. So to get the limiting reactant, what you can do is this. So 100 moles of F, and then per mole ng F, there's 10.10 moles of C3H6, and then based sa chemical equation, 2 mole of C3H6 equivalent to 2 mole of C3H3N. C3H3N because that's a product. Okay lang na, it's okay to use the H2O, pero wala, ito napili ko, C3H3N. So you can use H2O, no problem. And then that's 10 moles. 10 mole C3H3N. We will do this with NH3 and O2, and then we will going to compare the amount of C3H3N produced. Yung pinakamababa, the lowest, that's the limiting reactant. So let's repeat it with NH3. So 1 mole per 1 mole ng feed, there's 0.12 moles of ammonia, and then 2 moles NH3, that's 2 moles acrylonitrile, so that's 12 moles C3H3N. Next, we also have the O2 here, but the O2 will be coming from the air. So 1 mole of F, so per mole of F, there's 78% air, and then per 1 mole ng air, that's 0.21 mole O2. And then to get 2 mole of acrylonitrile, you need 3 moles of O2. So that should be around 10.92 moles. C3H3. So between the three, C3H6 produced the least C3H3N. So that means C3H6 ang limiting reactant. Okay, that's A. B, the percent by which the other reactants is in excess. Okay, so I'm just gonna write it here. Percent excess is number of mole fed minus number of moles theoretical over number of moles theoretical times 100%. So for NH3, number moles fed, that's 12 moles, that's 100 times 0.12. So 12 moles minus theoretical amount. The theoretical amount is based on the limiting reactant. So 10 moles C3H3N times that's C3H6. C3H6. And then for 2 moles of C3H6, that's 2 moles of NH3. And then that's the same thing sa baba. Times 100%. So that should be around 20%. And then percent excess O2. Percent excess O2, number of moles fed, that's 100 times 0.78. So let's just write it here. 100 times 0.78 times 0.21 minus, still based on the limiting reactant, 10 mole C3H6 times, based sa chemical equations, per 2 moles of C3H6, you'd need 3 moles of O2. Yeah. And then the same here. So it should clock around 9.2%. So that's B. Done. Letter C, the molar amounts of all product gas constituents for a 30% conversion. Okay, I don't have any more space. Letter C. C3H3N is this one. Ito na agad value niya. So, 10 mole C3H3N. And then, what you can do for H2O, we could just use the stoichiometric coefficient. So, for every 10 moles of C3H3N, 6 moles of H2O for every 2 mole C3H3N. That's 30 moles H2O. Next, C3H6. So C3H6, oh no. Okay. Okay. So for letter C, 30% conversion of the limited reactant, let's first determine that. Okay. So 100, so that's 10 mole C3H6, but only 30% will react. So that means 3 moles C3H6 reacts. So, pag exit, the exiting C3H6 is 10 minus 3. So, the 7 moles C3H6. Next, we can base from this one, the reacting C3H6, the number of acrylonitrile and H2O produced. So let's do that. 3 mole C3H6. Since C3H6 and acrylonitrile is in 1:1 mole ratio, so that's still 3 moles C3H3N. And then for water, 3 moles of C3H6. Now, based on equation, you'd need 2 moles of C3H6 to produce 6 moles of water. So that's 3 times 3, 9 moles H2O. And the next, the ammonia and oxygen, it's just this, the numerator part ng percent excess. So, exiting NH3 is 12 minus 10 times 2 over 2. So that's just 12 minus 10, 2 moles NH3. And then exiting O2 is 100 times 0.78 times 0.21 minus 10 times 3 over 2. And that should be around 0.21 minus 10 times 3 over 2, 1.38. Yeah. No, not that one. pala. This one, this one. Okay, that's it. Okay, that's example 1 done. Okay, let's move on to example number 2. So this one is multiple reactions. So methane and oxygen react in the presence of a catalyst to form formaldehyde. In a parallel side reaction, some of the methane is instead oxidized to carbon dioxide and water. The feed to the reactor contains equimolar amounts of methane and oxygen. The fractional conversion of methane is 0.95 and the fractional yield of formaldehyde is 0.9. The problem asks us 1. The composition of the output stream and the selectivity of formaldehyde to carbon dioxide production. Okay. Again, let's draw the diagram. This is the reactor. It says that the feed contains equimolar amounts of methane and oxygen. So, equimolar, that means equal amounts ang pumapasok. So, that would be 50% CH4, 50% O2, oxygen. This is F. And then this is the product stream. So in the product stream, there's CH4, there's O2, there's formaldehyde, there's water, carbon dioxide. Okay, and then the fractional conversion is 95%. The fractional yield of formaldehyde is 0.90. So basis, let's set a basis of 100 moles feed stream. Okay. If you have, kung meron given na single pass conversion or fractional conversion, you can use it right away. So since one of the requirements is the composition of the output stream, here's how we'll use it. 100 moles of F, and then we know that per mole of F, there's 50% methane, and then only 95% reacted. So that means 47.5 mole CH4 reacted. So if I have 50 moles in the beginning and then 47.5 lang ang nag-react, that means the difference is the unreacted. So the 2.5 moles unreacted, that's the one on the output stream. This one. Okay. Next, use the single pass conversion. Let's use the yield. So the yield is always based on the wanted reaction. So for example, the CH4O, the first equation, this equation, ito lang yung nag-exist. So that means 100 moles of CH4 times 0.5 and then per every mole of CH4, that's 1 mole of formaldehyde. So 50 moles formaldehyde. This is yung theoretical. Because remember, ang percent yield is or fractional yield is the amount actual over amount theoretical. So I have the yield here, I have the theoretical amount. I can solve for the number of actual. So that's 0.9 equals number of moles actual over theoretical, which is 50. So that's just 50 times 0.9. Actual number of moles is 45 moles. Formaldehyde. Let's tabulate it na lang dito sa gilid para masaya. Species and moles. And then let's do percent here. So for CH4, that's 2.5 moles out. For formaldehyde, that's 45 moles. Let's see, what else? Okay. This 47.5 moles CH4 reacted is split between the first and the second reaction combined. So to get how much CH4 is used for the second reaction, let's exploit the fact that I have the number of moles of HCOH dito. So 47.5 moles methane minus 45 moles of formaldehyde. And then, per 1 mole of formaldehyde, that's 1 mole of methane. So 47.5 minus 45, that's 2.5 moles methane for the second reaction. Now, I have that data. I can use it to get CO2. And, yeah, let's use it first for CO2. So, 2.5 moles CH4. And then, that's 1 to 1. 1 mole CH4, 1 mole CO2. So, that's 2.5 moles CO2. So let's write it here. 2.5 din CO2. Next. Let's do O2. Okay. So for O2, in the first reaction, there's 45 moles of formaldehyde. So let's see how much O2 is consumed. So 45 moles formaldehyde, and then per 1 mole ng formaldehyde, 1 mole ng oxygen ang needed. So that's 45 moles O2. And then for the second reaction, I already have the data from CH4 or CO2. So I'll use the CH4. So 2.5 moles. Oh, nawala. Okay, so I'll just flash the thing here. I'll just rewrite it later. So 2.5 moles CH4, and then that's 1 mole CH4, 2 moles of O2. That means that's 5 moles of O2. So from the previous one, I have, from the first reaction, I have 45 moles O2 used up. And then in this reaction, I have 5 moles of O2 used. So in total, I used 50 moles of O2. So how many is exiting? So that's 50 moles of O2 entering minus 50 moles of O2 exiting, I have 0 moles O2. So CH4, formaldehyde, CO2, O2, and H2O. So CH4, 2.5. This is 45. This is 2.5. 0. H2O. H2O na lang. Okay, let's use the 47.5 again. No, actually. Let's use the 45 moles from the formaldehyde. So 45 moles of formaldehyde. And then that's 1 mole formaldehyde. 1 mole H2O. So that's 45 moles H2O. And then, since meron ding H2O sa second reaction sa unwanted, we can use either the CO2 or the CH4. Let's use the CO2. 2.5 moles CO2. So for 1 mole ng CO2, 2 moles of H2O is produced. That's 5 moles H2O. In total, that's 50 moles of H2O. So you total that, that's 100. So this is 2.5%, 45%, 2.5%, 0%, 50%. So that's the answer for letter A. Letter B, what is the selectivity of formaldehyde to CO2 production? Selectivity is just the number of wanted over the number unwanted. So ang want mo daw dito is formaldehyde. So that's 45 over unwanted CO2, which is 2.5. So 45 divided by 2.5, 18. That's the selectivity. Okay? Okay. I think I have one more for this one. Yeah. A plant makes a very high grade lime by calcination of pure calcium carbonate in rotary kilns. In one kiln, the reaction goes to 95% completion. What is the yield in terms of kilograms of CO2 produced per kilogram of calcium carbonate? So it's just asking gaano karaming CO2 na po-produce per kilogram of calcium carbonate. So this is my reactor. Papasok is pure CaCO3. Lalabas CaCO3, CaO, CO2. So the single pass conversion is 95%. So what is the yield in terms of kilogram of CO2 produced per kilogram of calcium carbonate? Okay. So, CaCO3 is solid, but we can directly go with basis is 100. Well, let's just do 100 grams calcium carbonate because calcium carbonate is solid. Although we can do moles. Okay, to simplify everything, we will just do moles. 100 moles. 100 moles CaCO3. And then, the single pass conversion is 95%. So that means only 95% ng CaCO3 ang magre-react. So that's 95 moles CaCO3 reacting. So, since ang needed is kilogram of CO2 produced, let's do that. 95 moles CaCO3 multiplied to 1 mole ng CaCO3, that's 1 mole of CO2. And then 1 mole of CO2, that's 44 grams. And then we convert grams to kilograms by dividing by 1,000. So that's the CO2 produced. 0.95 times 44 times 1 over 1,000, 0.0418. 0.0418 kilograms. And then, since I already have that, and I already have the one other, let's see how much CaCO3 I have fed. So 1 mole CaCO3, that's 100 grams. CaCO3. And then 1,000 grams, 1 kilogram. 1, 2, 3, 4, that's 10, I believe. Yeah, 10 kilograms. Okay, so the yield is in terms of kilograms of CO2 over kilograms CaCO3. Okay, I double check. This is 4.18. Okay, this is 4.18 over 10. So that's just 0.418 kilogram of carbon dioxide per kilogram of calcium carbonate. That's it. Okay, last one. Aluminum sulfate is manufactured by treating crushed bauxite ore with sulfuric acid. The ore contains 55.4% aluminum oxide, and the sulfuric acid solution is 77.7% H2SO4. In one batch, 2,160, I think that should be pounds lang. 2,160 pounds of bauxite ore was treated with 5,020 pounds of sulfuric acid to obtain a final solution containing 3,600 pounds of aluminum sulfate. What is the percent conversion of aluminum oxide? So again, let's draw the diagram. It's 55.4% Al2O3, and then it is treated with 77.7% H2SO4. So the final solution contains 3,600 pounds of aluminum sulfate, 2,160 pounds bauxite ore. This one is 50-20 pounds of H2SO4 solution. So this is the ore, this is the solution, and this is the product. What's the percent conversion of Al2O3? Actually, this is a very simple one. This is very short. First, we need to determine which one is the limiting reactant. So it's between Al2O3 or the sulfuric acid. So let's see. limiting reactant. I'm going to try first Al2O3. The basis data given. So the limiting reactant, let's see, 2,160 pounds of the bauxite ore. And then, per pound of bauxite ore, that's 55.4 pounds aluminum oxide. And then we need to first convert the grams, the mass into weight, into moles. So that's 102 pound mass Al2O3. That's 1 pound mole Al2O3. And then based on the chemical equation, that's 1:1. So that's just 11.73 pound mole of Al2O3. Next, let's see about the H2SO4. 5,020 pounds of H2SO4 solution. Per 1 pound of solution, that's 77.7% pounds H2SO4. And then 1 pound mole of H2SO4, that is 98 pounds H2SO4. And then relate that sa aluminum sulfate. 3 moles of sulfuric acid will give me 1 mole of aluminum sulfate, and that's 13.27. Aluminum sulfate. So between the two, 11.73 pound mole is the lesser one. So that means the ore or the Al2O3 is the limiting reactant. So let me, ano ko nagawa yung kanina? Ayun. So the limiting reactant is Al2O3. Actually, that's yun yung pinapahiwatig nito. What is the percent conversion of Al2O3? Anyways, to get that, we need to know how much Al2O3 was reacted by using this. So 3,600 pounds of aluminum sulfate, and then let's see, per 1 pound mole of aluminum sulfate, that's 342.15 pounds of aluminum sulfate. And then from the chemical equation, 1 pound mole of aluminum sulfate, that's 1 pound mole of aluminum oxide. So that's 10.52 pound mole Al2O3 reacted. So percent conversion, number of moles reacted, 10.52 over number of moles fed, which is 11.73? Yeah, 11.73. Kasi 2,160 times 0.554 times 1 over 102. Yeah. Times 100% is equals to 89.68%. The percent conversion of Al2O3 is 89.68%. And that's it. That's it for the terms.